In this video, I'm going to go through a quick introduction of RAG. RAG stands for Retrieval-Augmented Generation. Now, if you've never heard of RAG, no worries. That's what I'm going to be doing in this video. The main idea is that when you use a large language model, but a large language model essentially is a model that was trained on certain data. So for instance, if you go to ChatGPT and you type in what is the capital of France, and of course it will give you the capital of France because it was trained on information about, including in this case, the capitals of countries in the world. But if you were to ask ChatGPT, what is the name of my first dog? Of course, ChatGPT wouldn't know because it's using that large language model, the model that was trained on something that is not related to your information that it is particular to you, that is specific to you. And that, of course, is indeed a problem. And RAG essentially allows us to take our own information, our own data, databases, video, textual information, raw data or unstructured data as they call it, sort of inject to the large language model. So now the large language model has more information, including your own information. And so now when you ask questions related to your specific data, you are able to get the answer from the large language model because it's able to connect to your data that you have injected. Happy day. So you get the right answer. So that is the idea of RAG. So that's what we're going to be doing in this mini course or in this video, and I hope you enjoy it. All right, let's go ahead and get started. In order for you to follow along in this course, you need to have your development environment set up. Particularly, I expect you to, of course, have Python set up on your machine. Also, VS Code or any other code editor of your preference, but I will be using VS Code, so I would encourage you to also use VS Code, but that is not a requirement. Also, make sure that you have an OpenAI account, which means you also need to have an API key. That way you're able to follow along if you want to actually do the hands-on with me, which I want to believe that's what you're going to be doing. So go ahead and have all those things set up and we should be good. Now, for you to set up the OpenAI API account, again, you can just go to openai.com and go through the process if you haven't done that already, and just set you up, create an account and create an OpenAPI key, which then we'll be using in this course. And if you are wanting to install Python, you don't have Python installed, it's very simple. Just follow this link and they have all of the things or all of the directions you will need to set up Python on your machine. So I encourage you to go through that and have everything set up. Okay, so they have Python for Windows, Mac, Linux, and everything. This is all in case you don't have anything set up. But go ahead and do that if you don't have that set up, and I'll see you next. All right, so let's go ahead and start doing the deep dive on RAG. So I know that most of you who are here may already know what RAG is, and that's wonderful. But I'm going to do just a quick deep dive overview so that we have some sort of a summary overview again of what RAG is. So we're going to look at what is RAG, the motivation behind RAG, and also advantages. Now, what is RAG? RAG stands for Retrieval-Augmented Generation. So the key points here is that we have retrieval, augmented, and generation. These are the key points here: retrieval, augmented, and generation. So the idea is that we have a system that retrieves information. We have also a way of augmented whatever we are passing through, as well as then push that information into a machine, quote unquote, that will generate a result. So RAG has two main components, which is the retriever. The retriever, what it does, it identifies and retrieves relevant documents. And then we have the generator. Well, it takes retrieved documents and the input query to generate coherent and contextually relevant responses. That's because that is the whole idea, to get coherent and contextually relevant responses. These are the main components of RAG. But we still haven't defined RAG really. So what is a RAG? So the definition will go as follows: a framework that combines the strengths of retrieval-based systems and generation-based models to produce more accurate and contextual relevant response. And we have the keys, again, the keywords, contextual relevant response, because that is the whole goal of RAG. Okay, that sounds great, but translating all of that, we would say efficient way to customize an LLM, a model, language model, large language model, with your own data. Well, what that means is, what are we doing really is that, as we know, a large language model like GPT and many others out there, they only know so much. Okay, so what we're doing is we are injecting our own data into this large language model so that it knows more than the things that it knows that was trained on. So now the large language model is going to know about specific contextual data in addition to what it was trained on. Let's look at an overview of RAG. We have documents. These documents are cut into small chunks, and then these chunks are put through an embedding large language model. So to create embedding essentially, and then that is what is created, embeddings, and those embeddings are set. Okay, so now the question or the query comes in, goes through the same process, transforms to embedding, and then we have this embedding, which then is used to go ahead and find in our retrieval system, in our vector database, most similar items, which then is pushed into a general large language model, which knows how to take that information, in this case, the most similar results with the question, in this case, the prompt, and get the response that is needed, that we're looking for. So that is how a RAG works. Notice here, when we say RAG, Retrieval-Augmented Generation, that means that the generated response is augmented by the data I retrieved from the documents in our case. Hence the name RAG. So really, if you want to do a deep dive into naive RAG, this is what happens. So we have the documents, and these documents are going through the phase of parsing and pre-processing. So essentially, cut them up into smaller documents. This is the chunking process, and then we pass them around into smaller chunks, and those are passed through the embedding model to create vectors out of these chunks. Okay, so we're vectorizing those chunks. And then that is what is saved into a vector store or a vector database. So this is the part of indexing that happens here. Of course, is the indexing part as I have shown you. This is the part where we cut the document and pre-process everything and chunk it up and then create those embeddings or vectorize those chunks and save them into a vector store. And then what happened is then we have a user who has a query or question of some sort, and that also has to go through the embedding model to vectorize that query. And then that is actually what is sent to search into the vector database. So we have vectors and vectors that are easily used in a vector database to do all sort of things, mainly to search. And then the information is retrieved. The relevant documents are retrieved, are packaged up, in this case with a prompt, as well as the relevant documents, as I said, and the query. But notice here, this is the different phase. This is the augmentation phase of the RAG. So we're augmenting, we're adding something to what we had before. So not only we have a query, but we also have really prompt, which is part of the query, and relevant documents, and so forth. Okay? So once that is augmented, we pass that information through a large language model. So it could be any kind of large language model, and then that's when the response is generated, which is then returned to the user. All right, so now you have the basics of understanding what RAG is, how really RAG works. The idea is that we have our own documents. We're going to go through the process of extracting those documents, splitting those up, and then pass them through the large language model. Of course, we're going to be saving that into a vector database. Now, if you don't know what a vector database is, I actually have yet another video where I talk about vector databases somewhere at the top here. Okay, so go ahead and check that out. So we're going to do a hands-on here where I'm going to show you how to use RAG to create a system, a RAG system that allows us to pass through some documents. And in this case, we're going to be a bunch of articles that we're going to be reading in, saving those to a vector database, and then perform RAG to start conversing, or in this case, querying our documents so we can ask questions and get the correct answers along with the large language model. In this demonstration here, I'm going to be using OpenAI which means that you need to go and have an OpenAI API key for you to be able to do this with me. Now, if you don't want to use OpenAI, you can use other large language models out there, and things will be a little bit different, of course, but the main idea is going to be the same. All right. Okay, let's go ahead and get started. And so I have this project called RAG Intro and I have a few things here. One of the important things is that you have here the OpenAI API key. So you need to get that. You need to have that. Then, of course, I have the app.py, which is empty at this point. So this is where we're going to start doing our magic. Now, before we do that, I need to make sure that I have a virtual environment. If you want to learn more about Python, I have a full video of 1 hour or so. You can go ahead and check it out. Also, you'll see somewhere here. All right. Or you can search on my channel. You'll find that. All right. So I have my virtual environment created there. And let's go ahead and say source venv and activate that real quick. So we have that set up. So now it's active. We are going to install a few dependencies. The first one that I need here, let's see, I have my cheat sheet here. So the first one that we need is the python.env. So pip install. I'm going to pass that. This is going to allow us to retrieve information from our virtual environment file. Okay. And then next I'm going to get the OpenAI because we're going to be using OpenAI. So I say pip install OpenAI. Okay, and because of the nature of large language models and RAG system, we need to save this information, this data that we're going to split up these documents into a vector database. If you don't know what a vector database is, I do have a course that talks about vector databases. And so there are many kinds of vector databases. We're going to be using ChromaDB, which is light and easy to use. So I'm going to say pip install ChromaDB as such, so we have that set up for us. I'm going to go ahead and import a few things that I need here. Now, just to make sure that this is fast, I'm not going to type everything because you should have access to this code. The OS, because we're going to be needing that to access operating system folders and files and so forth and other functions. I have ChromaDB and I have .env here to load all of environment variables. And of course, I'm going and importing embedding functions. We're going to use that to create embeddings because those are the representations of our data that we need to have in order to put that into our database, vector database. Of course, we have OpenAI here, which we're going to be using soon. All right, so next what we'll do here, I'm going to load all of our environment variables, and then I'm going to set up the OpenAI key from my environment variable, as I said, from our environment variable, from our environment file there. And then what we're going to do is we're going to create the function, the embedding function. This is what it's going to allow us to create those embeddings again. Once we chop up all of our data, which I'm going to show you in a second here, we want to transform that into embeddings, these zeros and ones, a vector space, and then that is what's going to be saved into the vector database, the Chroma vector database. And when you do that, when instantiating this embedding function, you need to pass the API key, OpenAI key, because it needs to know what model it's going to be used to do that. And we're going to pass the actual model name, which is going to be text embedding 3 small. So this is just a very small, light embedding functional system that allows us to create embeddings. And next, I'm going to go ahead and, of course, initialize the Chroma client persistence. So I want to be able to persist, or in this case, I want to be able to save the actual database. Now, looking at the data here, you see that I also have these news articles. So this is where I have all of these articles, news articles that I found online. This is what we're going to be using as the documents. And then we are going to chop it all up, put it into a database, right? Not a normal database. This is going to be a vector database. And then we're going to use other techniques to start conversing, talking, and getting the documents that we need to answer the questions that we are asking. So what are we doing here? We are initializing the Chroma client. You can see it's very simple, really. You say Chroma persistent client, and then we pass the path we want this to have. Now I said Chroma persistent storage. This is kind of long, but you can make it shorter if you want. And then the collection name, we add whatever name we want. And then now we actually say Chroma get or create collection, which means this function allows us to create the actual collection. Collection is just a table or a document where we can put all of these documents or tables in this case, okay? And then we need to pass the embedding function. Notice that now we are passing what we initiate or instantiated at the top here, the actual OpenAI embedding function that is going to allow us to create those embeddings, right? The vector embeddings along with the collection name. There we go. So now we have this collection that indeed we created with Chroma. All right, so let's go ahead and create our client. This is our OpenAI client. We pass the API key and the OpenAI key, of course. So now we have our client. We can do all sort of things, meaning we can, for instance, say client dot, I think it's chat dot open, what is that called? Completions, and I can go and create, and then here I can pass a few things such as the model, I believe. Let's say model, and I can say GPT-3 Turbo, and I can pass messages and roles and everything. In fact, let's just do that real quick here so you can see this client working. You can see we have the messages, and the system says you're a helpful assistant. What is human life expectancy in the United States? Well, that's pretty good. Let's go ahead and see if this works, making sure that you have everything set up, of course. So I'm going to say print. Actually, let me put this, say res or resp like this, and say I can say resp like that, and I can go to choices and go to message and to get the content. All right. So if I go ahead and run this, I should be able to get something. So Python like this. So should let us know that indeed we have everything set up, and we should get some results in a second. Okay, looks like we have some issues here. Resp, choices, message. Let's just go and get the response, the whole payload. I think I'm missing the actual object. It's okay. Let's run again. Okay, so we can see that we have the response chat completion, and went ahead and got, as of 2020, the average life expectancy in the United States is around 78.8 years old, and so forth. Okay, so we're getting a payload to tell us that this is actually working. Okay, of course you can get to the actual payload if you want this content here. If you go through, I can go straight to content, I believe, like that. Okay, same thing. Go ahead and run. We should get the actual content, I think. Okay, there we go. So now we get the actual content as of 2020, blah, 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 and so forth. Okay, so at least we know that this is working. That's all we really wanted. That's not our end goal, so I'm going to get rid of that. Okay, so the first thing we need to do is, of course, to load our documents from our articles. As you can see here, we need to load all of them and then start doing something. So I have all of the code already so that we don't spend too much time, and you'll have access to all this code anyway. And what I'm going to do, it's a function that I created before this. So what are we doing here? We're loading documents from a certain directory. So I have a print statement here just to give us what's happening. And I go through, in this case, I know that all of these articles documents end with txt. They are txt files. It's kind of hard to see. You just have to believe me. You can see here, they are txt files. Okay, so that's what we're doing. We're going through and start loading all of them and return the actual documents, right? It's going to be a list of documents. All right, so the next thing is we need to split these documents. Once we get them, we're going to have to split them up so that then we can pass them through into our database. So I already have a function that does just that. You can see we pass the split, the text, and we say the chunk size is 1000 and the overlap is 20. The overlap essentially says once we split these documents, we want to make sure that they overlap, right? Overlap like this. That way the contextual meaning of each piece of text is overlapped, which means it's kept, the context is kept. Because once we split all this up, these documents in small chunks, they're going to be very distant. So the more overlap we have, you can see that the more context we'll have kept. The less overlap. So that is the idea, really. And so we just go through the splitting process and then we return the chunks. Okay, so we have those functions we're going to be using soon. And so now we're going to go ahead and load documents from the directory. So the directory, as you see here, is, let's see, right. I should have said news articles. Okay, so I'm just going to remove this like that. Should have put under data, but it's okay. So is under news articles, which is this guy here. And it's going to go ahead and get all of them. And then for the documents, I'm going to go and then I'm going to call load documents from directory, pass the path, which is this one here. And at this point, we should have all the documents. I'm going to go ahead and print real quick here so we can hopefully see. We should have the length of the documents once we have those documents loaded, right? So in this case here, you know that this should return a list of documents because documents is indeed a list. Okay, we should have something. So let's go ahead and save this, and I'm going to quickly run again. Okay, loaded 21 documents. Very good. So it went and got all of those documents that we loaded in. Essentially, all of these documents here. So they're about 21. Now, once we have these documents, of course, now it's time for us to do something else. What we need to do really is to get those documents split up. So I'm going to go ahead and do that. So now I create the split documents into chunks. So I have a list and I go through those documents that we just received, and then we call this split text. Split text is indeed what we have here. So it's going to go through and return another chunks, which is a list of all those documents that are split. But remember, we have this overlap for each document to continue having the context. Okay, very good. So we do all that stuff, and then I can go ahead and say print again, split documents. So this should give me all of the documents chunks, split documents into the length of chunks, okay? Because I should have something at this point. Let's run again. Okay, so you can see it went through the process, splitting docs, and this is telling me how many splits I got because that is what indeed I asked, length and so forth. Okay, so we know this is working, which is essentially what we want. Okay, so the next function I need here is a function that will generate those actual embeddings. Because remember, once we split up all the documents, we need to take those splits that we did here and create embeddings. This is what's actually saved into our database, into our vector database. So I have a function here that is going to be helpful for us to use. So essentially what this does is we use OpenAI to create those embeddings from the text. Okay, that's what we're doing here. So you can say client, embeddings, and create, and we pass the text, these pieces that we are putting through, and then we say the model that we want to use to create those embeddings. That's all we're doing here, and then we get those embeddings and return them. Okay, this is going to be helpful in a second here. Then I'm going to generate the actual embeddings. Why? Because I already have the function. So to generate embeddings, we go through all the chunked documents. Yes, you remember these guys here. And then as we go through, we call these get OpenAI embeddings, and we pass the actual information through to then create a document embedding field. So each time we go, we're actually creating those embeddings. So we can actually print to see our embeddings. So I can say doc embedding, and what will happen is, let's go ahead and run real quick so you can see. We're going to go through the whole process, splitting, and look at that. It's creating those embeddings. It'll take a bit, and in a second here, we should see actual embeddings. So after a little while, so be patient, but this will take a while. You can see now we have the embeddings for vector spaces, right? And so there we go. Of all the documents, now we have all the embeddings. This is these vectors that actually we're able to then add to into the database. So this is good. So I'm going to go ahead and clear this. So I just wanted to show you. Okay, so now that we have our embeddings, let's go ahead and comment this out so we don't run that. Let's go ahead and insert each one of these embeddings into our database. Okay, so of course I have the code for that. So for each one of these, we're going to, because we know these chunked documents, which is what we have here, it has all of the information. What we do now is that we're going to get those chunks, the real chunks, before we embed anything, add into our vector database, And at the same time, we're going to add the actual documents along with the embeddings. So now we're going to have these chunks of the documents, these little pieces, not embedding. These are just the text chunks. And then we're going to have the actual embeddings. They are going to be sitting on our database. Oh, very cool. Then we're going to create a function to query our documents. So I have all of that, and I'm going to just copy that and put it here so we don't have to do all the things. So the idea here is that query documents. And now this query documents is very simple. We pass in the question like, tell me about GPT-4, something like that. Anything pertaining to our data that we've just saved, okay? And then we say how many results we're expecting to receive, how many documents essentially. Because what will happen is we're going to be able to retrieve the documents corresponding to the query that we're passing in, right? So in the background, what will happen is the database is going to be able to go and search, do similarity search until it finds what is congruent with the question that we have inserted. That's pretty cool, right? And so we say in collection.query, passing the question and the number of results we want, documents that we want, and then we put in a variable. And then we extract the relevant chunks from that, from our list of documents. Because this result here is going to have the list of documents. That's why we can go through those documents and get the relevant chunks. And then once we have them, we just return those relevant chunks. I have this other code here. You can check it out. This is going to just give us the distance between the relevancy. So essentially tell us how close to the actual answer these documents are, okay? And you can play with that. Okay, so next, what we'll do once we have this done, I'm going to then, of course, have a function that will generate the response. Because think about it, we have taken the documents that we have, we chopped them up, we put them, we created a vector database, and then we put inside of that vector database. But before that, we're able to create embeddings because we want to save those embeddings because it's easier for the search to happen, right? For the right document once we ask the question. And so now we want to generate the actual response. So now we are going to use the large language model again, OpenAI in this case, to do all of the work with all these pieces that we have right now. So as you can see here, we pass in the question and we need the relevant chunks. Right, we are taking the relevant chunks that we created. We were able to query the database, right? And then we are passing that along in this with the question. So now we have the question, our question, asking questions about these documents, right? Whatever. And then now we have these only relevant chunks that were passed through the large language model, and the large language model now has more information or more knowledge of what we want to get the answer from, right? And so that is what's happening. So here I'm creating the context. So essentially, I'm getting these relevant chunks and joining in with other stuff. And then I have a prompt here, a prompt for our large language model to say, hey, this is what you need to be aware of when you are answering these questions. You're an assistant for question answering tasks. Use the following pieces of data, blah, blah, blah. Retrieve context to answer question. If you don't know, please say, I don't know, and things like that. Now, prompt is actually its own thing, and you have to be really good at prompting to get the right result from large language model. And then, of course, we pass that context and the question. We need to pass those two things, right? So now the large language model will have the question that we're asking, we typed in, and then we'll have the relevant documents because we've parsed that through already. You see? Okay, and then we call the create again. We go to the client, chat completions, and create, of course, the actual. Now we are going to the actual model. Say, hey, here's the information. Go ahead and give me the answer. That's all we're doing here, okay? We pass in the prompt and as well as the question, and then we get the answer. This is what this will return. So now it's time for us to check out to see how this will work. So now I'm going to have here this query that I'm going to start doing here. So here, example, question. Tell me about AI replacing TV writers in strike. Now I know this question that would work because in one of these documents here, we talk about AI replacing jobs and so forth. And so I'm going to see if this works. So here's what's happening. I have the question and I need to get relevant chunks, right, from the document, in this case from the database. Well, I call the query documents and I pass the question. So it's going to go ahead and query the documents that are in a database, finding documents that are relevant to the question that we're asking, which is this here, right? And once we get these relevant chunks, we're going to need that along again with the question, the first question, and the relevant chunks we got to get the answer, right? Because this generate response here, this is what we just talked about, is going to go ahead and pull in the context, relevant chunks, as well as the question, create a prompt, and then pass that through that prompt, and then call the large language model to then answer that question, and we get that answer. Okay, let's see if this works, and then we're going to print the answer here. All right, let's run this again and see if this works. So you're going to go through the whole process, of course. It will generate everything. And one thing also in the beginning, of course, we'll go through the process, but once you run once, because we'll have that data and everything, we should be able to just comment out the first part of this code, essentially. So everything is good. But in any case, everything will still work, should work, because we have that data already. The other thing you will notice is that now we should have, you can see now we have this Chroma persistent storage, which is indeed the Chroma SQLite 3, which is the database that we created. This is the actual Chroma database. Pretty cool indeed. Okay, so we have that set up. So this will take a little bit, of course. Okay, now it's saying it's retrieving relevant chunks, and voila. It says here, TV writers are currently on strike due to the Writers Guild of America demanding regulations and the use of, on the use of AI in writers' rooms. So the Writers Guild, blah, blah, blah. So all of this information actually pertains to the articles that we have here. So AI replace TV writers. If I click here, you will see that indeed I should have something related to that. Let's see. Okay, regulate the use of AI, non-clear work, and so forth. So it goes ahead and looks at the correct other ones here that relate to exactly that. So for instance, I can go ahead and ask something else. Let's see. Let's say something about Databricks. Okay, so let me say, tell me about Databricks. And let's go ahead and go through the process. It went through the whole process, inserting chunks into DB, blah, blah, blah. It went through all of that. We know that. And at some point, it went ahead and say returning relevant chunks. And then, of course, we hit the large language model and says Databricks is a data AI, an AI company that recently acquired Okera, blah, 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 and so forth. So just like that, we're able to take the information, our own data, in this case here, so this could be anything, our own data in this case, and we parsed all that through. We extracted everything. We created these little chunks of this data, and then we used OpenAI API to actually create the embeddings. That's very important. And then we save that into a vector database. This is very important also. This is not a normal database. This is a vector database. And then we're able to search that vector database according to the question that we're passing through it. And then we got the right chunks, right? And then we pass those chunks of documents and the question and pass that through the large language model. And then we're able to get the answer. This is the power, as you see here, because now we're able to take our own data and sort of inject into the large language model so that we are able to ask questions about our particular data. And I hope you can see so many use cases that you can use this particular RAG system here to help you with analyzing data and so forth. All right, so now that you have the basics, the fundamentals of RAG, how to create a simple RAG system that allows you to converse or chat with your own documents, so essentially injecting some information, your custom information, your data, with the large language model so you can converse and start talking, chatting, and getting conveniently response that is attached or that is congruent with your own data. Okay, so you know how to do that. And of course, now you know how to create, of course, a database, a vector database, which is very important for us to be able to save those pieces of information of our data, documents in this case, and then save all of that information along with the embeddings, which is really important because all of this is being saved in a vector space, which is easier for the vector database to be able to find things faster, things that have meaning and relevancy. If you don't think about it, you think that this is where it ends. But obviously this is not where it ends, because you will see that RAG, as it is right now, we call it naive RAG. It has its own pitfalls. And so now we are ready to move forward and learn of these pitfalls that naive RAG, which is what we've been doing, the pitfall that it has. And then we're going to learn and implement a technique or certain techniques that will take our RAG system to the next level. Okay, so we can actually get consistent results, because as it is, you can get some results that are not very consistent and results that may not be necessarily congruent or related semantically with your query. And that is what we're going to be touching on next. Okay, let's go ahead and do that. So naive RAG is the most simple, straightforward way of dealing with large language models. So essentially, it has indexing, retrieval, and generation. So indexing, it is the process of cleaning up and extracting data from the documents, just like as we saw earlier. And then we have the retrieval. So this is the part where we turn questions into a vector space, and that's what's used for comparison, which allows us to retrieve closely related chunks, which then are pushed with the query into the generation phase, which then the query, chosen documents, are combined into a prompt. So we have a prompt, the query, and the documents that were chosen pushed to the model to generate an answer. So this is the naive RAG. So really, if you want to do a deep dive into naive RAG, this is what happens. So we have the documents, and these documents are going through the phase of parsing and pre-processing. So essentially, cut them up into smaller documents. This is the chunking process, and then we pass them around into smaller chunks, and those are passed through the embedding model to create vectors out of these chunks. Okay, so we're vectorizing those chunks. And then that is what is saved into a vector store or a vector database. So this is the part of indexing that happens here. Of course, is the indexing part, as I have shown you. This is the part where we cut the document and pre-process everything and chunk it up, and then create those embeddings or vectorize those chunks and save them into a vector store. And then what happened is then we have a user who has a query or question of some sort, and that also has to go through the embedding model to vectorize that query. And then that is actually what is sent to search into the vector database. So we have vectors and vectors that are easily used in a vector database to do all sort of things, mainly to search. And then the information is retrieved. The relevant documents are retrieved, are packaged up, in this case with a prompt, as well as the relevant documents, as I said, and the query. But notice here, this is the different phase. This is the augmentation phase of the RAG. So we're augmenting, we're adding something to what we had before. So not only we have a query, but we also have really prompt, which is part of the query, and relevant documents, and so forth. Okay. So once that is augmented, we pass that information through a large language model. So it could be any kind of large language model. And then that's when the response is generated, which is then returned to the user. So this is how naive RAG works. As wonderful as this sounds and looks, there's some issues with this. Well, naive RAG has some challenges, some pitfalls, some drawbacks. The first one is that we have limited contextual understanding. So for example, if a user asks about the impact of climate change on polar bears, so a naive RAG might retrieve documents broadly discussing climate change on polar bears separately, but will fail to find the most relevant documents discussing both topics in context. Okay, so that is a problem, because naive RAG models often retrieve documents based solely on keyword matching or basic semantic similarity, which can lead to retrieving irrelevant or partially relevant documents. And then, of course, we get inconsistent relevance and quality of retrieved documents. So what that means is that the quality and relevance of the retrieved documents can vary significantly because naive RAG models may not rank the documents effectively, which leads to poor quality inputs to the generative model. And the third one is that we have poor integration between retrieval and generation. What that means is that in naive RAG systems, the retriever and the generator components often operate independently without optimizing their interactions. So you can see two things are working independently. They're not optimized to work together. That's a problem. So this lack of synergy could lead to suboptimal performance where the generative model doesn't fully leverage the retrieved information. So as an example, the generative model might generate a response that actually ignores critical context that was provided by the retrieved documents, which in this case will result in generic or off-topic answers. Also, we have inefficiency handling of large-scale data. Naive RAG systems may struggle with scaling to large datasets because of its inefficient retrieval mechanisms, which leads to slower response times and decreased performance. For example, in a large knowledge base, a naive retriever might take too long to find relevant documents or even miss critical information due to inadequate indexing and search strategies. We also have lack of robustness and adaptability. The issue here is that naive RAG models often lack mechanisms to handle ambiguous or even complex queries robustly. So they're not adaptable to changing contexts or user needs without significant manual intervention. You can imagine if a user query is vague or multifaceted, a naive RAG might retrieve documents that partially address different aspects of the query, but fail to provide a coherent and comprehensive answer. Okay, so these are some of the main drawbacks or challenges or even pitfalls of naive RAG. Okay, let's go ahead and break it down, each one of these pitfalls of naive RAG, so we can have some better ideas, okay? So let's look at the limited contextual understanding as we focused on in the last lecture. How does that even look like? Again, we understand in naive RAG, limited contextual understanding, focus on keyword matching or basic semantic search, in this case, retrieving irrelevant or partially relevant documents. So essentially, as I said, we have a query, for instance, that says the impact of climate change on polar bears. And so the idea is that that question is transferred through the whole process, this naive RAG, which we don't have to go through the whole details of what happens there as we know it. So this is just an illustration. Goes through all of that, and then it just retrieves non-relevant docs on both topics. Okay? So that is the limited contextual understanding that is lacking, which is one of pitfalls of naive RAG. Okay? Because naive RAG models often retrieve documents based solely on the keyword matching or basic semantic similarity, which you can see here can lead to retrieving irrelevant or partially relevant documents, non-relevant docs on both topics. Now, the next one we talked about is the inconsistent relevance and quality of retrieved documents. So the problem is the same. With naive RAG, we have this plethora of varying in quality and relevance documents, which means we have poor quality inputs for the model. Again, the same example, we'll have a query that goes through and that says latest research on AI ethics, for instance. And so that goes through the naive RAG process, and then we may end up getting outdated or less credible resources because the quality and relevance of the retrieved documents can also vary significantly. So naive RAG models may not rank the documents effectively, which in this case will lead to poor quality inputs for generative model, which in this case, will get very poor results. The next one is that we discuss is the poor integration between retrieval and generation. And so we know that because of the nature of naive RAGs, the retriever, I should say, and the generator components often operate independently. They are operating alone without optimizing the interactions within themselves, which, as you know, if two systems are working not in conjunction, the synergy can lead to suboptimal performance, which means we end up with very unoptimized documents or information that is being passing through. So again, we have in this case the retrieved documents, and these retrieved documents are of course used through the naive RAG system. And what happens is that we may lose what's actually important, what is relevant, and we end up with very generic or even off-topic answers through this whole process, because these two systems are working. The generator, in this case the generator and the retriever, are components that are working independently without optimizing their interactions. And the next one is inefficient handling of large scale. Let's look at the overview. The idea is that using naive RAG systems, these tend to struggle with scaling to large data sets because of the inefficient retrieval mechanisms, which lead to very slow response times and, of course, decreased performance. Because it takes too long in larger scale data, of course, sets and so forth, to find relevant docs, which of course leads to missing information due to bad indexing, essentially. So essentially it's the same thing. We have the index process, which creates, of course, this index data structures, which then, in the grand scheme of things, is going to have trouble trying to find the right information in a very large knowledge base if you have a lot of documents and so forth, because it's taking too long, and of course it may end up missing critical information because of these inadequate indexing and search strategies. Okay, so going to the lack of robustness and adaptability. This is another one. Models often lack mechanism to handle ambiguous or complex queries. So remember that queries are not always very direct. So you can have a query that is loaded per se. It's ambiguous. It has more information, more questions. That's a little bit complex. So with the naive RAG, they don't just have the mechanisms to handle that, because they're not adaptable. So that is the problem. Here's an example. So we have a query, tell me more about index funds and anything related to finances. So this is a little bit loaded, this query, isn't it? As you can see that naive RAGs don't have a way of deciphering through this query to get to the bottom of the actual query, or to get the correct, coherent, and comprehensive answer. So these are the drawbacks, doing a little bit of a deep dive into each one of the drawbacks or challenges or pitfalls of using naive RAGs. So in summary, naive RAGs have, of course, some pitfalls, as we've seen. And we can subdivide those pitfalls in two categories. We have first the retrieval challenges. So in this case, they lead to the selection of misaligned or even irrelevant chunks, which of course leads to missing of crucial information, which, as you know, it's not a good thing. And then we have the other side, which is the generative challenges. So under this umbrella, we have issues that the model might struggle with hallucination and have issues with relevance, toxicity, or bias in its outputs. So these are the two umbrellas, I would say, of the drawbacks that naive RAG brings to the table. Retrieval challenges as well as generative challenges. Now let's talk about the solutions here. In this case, we are going to go from the naive RAG that we've looked at and its pitfalls. Now we're going to look at advanced RAG techniques that help us make this whole process more efficient, okay, for our RAG. And so advanced RAG techniques and their solutions. Now let's look at the first one. Now first, let's look at advanced RAG's benefits. What is it important? The beauty here is that they introduce the specific improvements, this plethora of improvements that allow us to overcome the limitations of naive RAG as we've seen previously. The main goal here is that with advanced RAG benefits, we are focusing on enhancing retrieval quality. So advanced RAG employs the following strategies. The first one is pre-retrieval. So the idea is to improve the indexing structure and user's query, because that is very important. The first step, if you don't have good indexing structure and user's query, then everything else falls apart. And also, we're going to improve the data details, in this case, organizing indexes better, adding extra information, augmentation, part of it now, and aligning things correctly. And then we have the second part, which is the post-retrieval. At this stage, we are combining what we got from the pre-retrieval stage, okay, the data that we got there, with the original query. So we're combining all of that to finalize this augmentation part of the RAG. In this case, we could be re-ranking to highlight the most important content, or doing all other techniques goes ahead and to enhance our retrieval processes. Now, there are many advanced RAG techniques out there, have done a lot of studies and written papers that you can go and take a look. One thing I'll let you know of is that as you go through all of these other different techniques, even beyond this course, you will realize that most of them tend to overlap, and sometimes the namings can also overlap. And that's okay, but the main idea is the same, which is having techniques that allow for a better workflow of our RAG systems. So the first one we're going to look at here is the query expansion. In this case, it's going to be with generated answers. What does that really mean? It's that we're going to generate potential answers to the query. In this case, we're going to actually use a large language model to get relevant context. So with the query expansion as an advanced retrieval technique, it's used to improve the relevance. Again, keep in mind these keywords. It's used to improve the relevance of search results by augmenting the original query with additional terms or phrases, because these additional terms are selected based on various strategies such as synonyms, expansion, related terms, or contextually similar words. So the goal is to really capture more relevant documents that might not match the original query. Terms in this case will not match them exactly, but are semantically related. So to show you here, here's a simple diagram. So you have a query, and this query has to go through a large language model to create an answer. This is I would call an hallucinated answer. Okay, and then we take that answer that goes through the vector base, and then we concatenate the answer and the original query and use that as a new query which you pass through the vector database, in this case the retrieval system, and then you return your query results, which was passed through the large language model again, to get the actual results, the answer. So that's all we're doing here, is that we are using the large language model in this case to hallucinate a little bit on that first query, and then we concatenate the original query, or in this case the answer, that answer that we got, right, and the original query, and use that as a new query, which then we pass through the vector database, the retrieval system, and then return the query results again, pass those through the large language model again to get the results. So what happens here is that with this expansion here, we have a few use cases, right? This query expansion with generated answers. We can use that in the information retrieval. You can imagine with the system now we can enhance the effectiveness of search engines because we're providing more comprehensive search results, and also in question answering systems because now we are improving the retrieval of relevant documents or passages that potentially help in answering user queries. In e-commerce search, because it increases the accuracy, right, and relevance of product search by expanding user queries with related terms. Academic research, it makes sense because now we are able to find more relevant papers by expanding their search queries with related scientific terms and concepts. Okay, so let's go ahead, do a hands-on. So essentially, again, this is the diagram. We have the query, pass that through a large language model, and we get an answer. So a hallucinated answer, and that's okay. But that's going to be used, of course, concatenate with the answer and the previous query, and we get some results from our vector database, which then we pass all of that into a large language model, and we get an answer. So in the next video, we're going to see how all that works in code. Okay, so I have a project here. You should have all access to all of this code and data and everything. And at the top here, we have this data folder, which has this Microsoft annual report. Okay, so if you click on that, it's just a large PDF with about 126 or 116 pages. So it talks about Microsoft annual report 2023. Okay, so I just found this and I thought it would be a good idea to use that for our demonstration here. Okay, so we'll have access to all of this, and also make sure that you create a virtual environment on your project so this works, as well as having, in this case, an OpenAI API key. You should be able to go and create an account with OpenAI and get a key, so if you want to follow along. And so forth. I've got this helper utils, other utility methods, and so forth. Okay. All right. So the first thing, let's go ahead and do some importing here, or installing some dependencies. First, I'm going to say pip install chroma db, because that's what we're going to be using. And next, let's do pip install PyPDF, because we're going to be using that as well to read a PDF file and extract everything. And let's go and say pip. I'm going to install OpenAI. Okay, so let's go ahead and create a new file here. Let's call this XP. Say expansion, insert.py. Okay. All right, so I already have the code, so I'm going to just get parts of it and we go from there. First, I'm going to add some imports here. Get a PDFy. Let's make sure that everything is set up. Okay, we got our PyPDF, PDF reader. We have OpenAI, all of that, and I'm going to set up the environment variables as well. So OpenAI API key. Make sure you have that set up inside of yo.env file. It's very important. First, let's go ahead and read our Microsoft annual report. It's under data. You can see it's under here. Okay, should have access to all of that. So that's what we're doing here. And then PDX text, I'm extracting everything from the pages. Filter the empty strings real quick. And while I'm here, let's go ahead and run this real quick to see if this works. I'm going to just print this PDF text that we get here, filter out the empty strings. And I'm passing through the word wrapper so we can see. So I'm going to print that out. Let's see what's going to happen. Let's go ahead and run this. Okay, so I need to import panda as pandas. So that's something. Okay, make sure you import pandas as well. Let's go ahead and run. Okay, so we can see that we're able to extract our PDF and we get all of that response. So this is really good. Okay, so now that we have the information that we need, which means we extracted the text, I'm just going to comment this out. We extracted our PDF. We got all that information from our document. What we need to do next is we want to be able to split the text chunks. And to do that, we're going to use LangChain, which is a framework that allows us to deal with large language models and do all sort of things. Okay, so first let's go ahead and get that. So pip install LangChain. LangChain splitter as such, so I can go ahead and get the recursive character splitter as well as the sentence transformers token text splitter, because we're going to need those two before we get everything and start embedding everything. Okay, so let's go ahead and take care of splitting our document using the recursive character text splitter, which we are passing the chunk size 1000 and chunk overlap of 0. And then here we are splitting the text by getting all of the actual PDF text that we have created from here. Okay, so taking that, this is where we're splitting it, and we're going to get the character splits. So I can also come back here. I'm going to print the character split text, all right, the 10th one, and then I'm going to show the total chunks. So I'm going to save this and let's do a quick run. Okay, so you can see that we have indeed the information that we wanted to see, this word wrap of the character splits, right? In this case, just the 10th one. And we see that's the one that we got. And then we have total chunks is 410 chunks that were split. That's very good. Next, we use the sentence transformers token text splitter to split the text into chunks of about 256 tokens. And then we're going to set the chunk overlap to 0. Okay. Now, the reason why we need to do this is because we need to be mindful of the token size for limitations that the large language models could impose. Then we'll be able to use to generate the embeddings which we need. Okay, so let's do that. So here I'm creating the token splitter by using the sentence transformers token text splitter. And I'm passing overlap 0 and the tokens per chunk 256. And then we're going to go ahead and actually start doing the splitting. So here I create the text token split text, and I loop through all of the pieces and I split them up. And now let's go ahead and print some information out so we can see the difference here. So I'm going to save this. So notice the first one, the total chunk, when we first did it all, right, about total chunks is 410. And now you can see the difference that for the chunk, the total chunk is going to be a little bit elevated, which makes sense. Okay, so looks like could not import sentence transformer from Python packages, need to be ordered sentence. Okay. Yes, I need to go ahead and install. That's right. So let's go ahead and say copy that. And first of all, say pip install sentence transformer. So we have that. Okay, we have that. Let's rerun this. Okay, so first we have the 410 total chunks, but next we should have a little bit more because of what we just did. Okay, so you can see it's a little bit more now, 419 as opposed to 410. So very good. So that is the total chunks of the splits that we did here. Okay, this is the token split text. Okay, so now it's time that we have, since we have all the tokens, we can go ahead and start the embedding process. So first of all, we're going to import ChromaDB, and then we're going to use ChromaDB and get the embedding function. We could have used some other embedding functions using OpenAI and so forth, but I'm going to use the sentence transformer embedding function for this demonstration here. So we're going to import that, and then I'm going to actually instantiate the sentence transformer embedding function, as you see here. And just because I want to see, I'm going to go ahead and print the token splits token, because it's come as a list, the 10th one here, the 10th chunk, to show, so we can print the actual embeddings of the 10th chunk. Okay, so just to avoid having a lot of things printing out, I'm going to just comment out all of these other that we had before. Okay, so you can see now we have the embeddings for the 10th chunk. Okay, not very useful, but at least we see that things are actually working. So the embedding function is indeed working. Okay, so we know that the embedding function is working, so we no longer need to see it. So I'm going to comment this out. I'm going to leave it there. And next what we'll do is we're going to instantiate the Chroma client and create a collection and give it a name. And passing, of course, the embedding function so that we can embed each one of these items that are passed along. So Chroma, I'm going to create a client and then create a function. In this case, I'm going to just give this Microsoft collection. You can name whatever you want. And then embedding function is going to be passing the embedding function, which is going to be attached when we create the Chroma database. Okay. And once we have that, we can extract the embeddings of the token splits by just going through like this. Okay. And then we are going to use that where we get all of these embeddings of the token splits, and that's what we're going to be adding to our collection, right? So to do so, I'm going to just copy this. To do so, we do this. So we say chroma.add, and we're going to add these IDs as we go through, and the actual documents. So the documents are going to be the token splits, right? And I'm going to just say chroma collection count. And for now, let's go ahead and print, just say count, and say count like that, so we can see. Okay, so you can see the count is 419. So essentially what we had before. Very good. So at least we know that it's working. Okay, so I don't need to do any of that. And so what we'll do next is we're going to create the actual query. We've extracted the document, split it all up, and then added that, putting that through an embedding function. So we have the embeddings, and then we added all of that inside of our Chroma DB, okay, our vector store. So I'm going to have a query here. What was the total revenue for the year, for instance, right? And then what we'll do is we're going to query using the collection. So collection, the query, we pass the query text, which could be, we could pass more than one query. That's why we pass as a list, and then the number of results that we want to get. Okay, and then retrieved documents, I'm going to say results and get the documents as such. And so what I will do is, for us to be able to see, I'm going to loop through all these documents so we can see what we get. Let's run again. All right, so you can see that we got some of the documents. Okay, so very good. Revenue and this year, and of course these are split up, and that's the whole idea, is that they may not make sense or where they start, but you can see we have 1, 2, 3, 4, and a few documents that we're getting here. All right, so this is indeed working. So now we know we're getting all the documents. So it's a matter of trying to figure out, okay, how do we see how this technique works? Meaning that the first query, and we get the documents that we've just retrieved, and as well as creating, in this case, we're going to generate the actual queries, right? The augmented queries we see, because that's the whole idea of this technique. Okay. First thing is I'm going to create a function called augment query generator. So this is where I'm going to use the augment query generator to generate an actual answer. So we're going to use, of course, a large language model, in this case, OpenAI, and generate this actual answers, or one answer in this case. So first of all, I'm going to have to create a client for OpenAI. So I'm going to copy that. And so this augmented query generator, what it does is allows us to pass the query, and we're setting up the model to be GPT-3.5 Turbo. You can change that if you want. And then I have the prompt here. You are a helpful expert financial research assistant. Provide an example answer, because we want an answer to given question that might be found in a document like an annual report. So we're prompting it, making sure that it knows what to do. And then we pass the message here for the prompt here for the system is where we created here to know this is what you need to do, what you need to be knowledgeable on. And then we pass in the query. So the query is going to be the question, the first query that we pass along. Okay. And then we use, of course, the completion API that create, pass in the model and the message, and we get that response. So essentially here, so this is where we are looking at this part here. So we're going to generate this one answer, which we're going to take with the query, the answer we got, go through our DB, and we got the query results, and then put all of that together into the large language model and get the answer. All right, so we have that function which we'll be using soon. Okay, so next what we'll do here is we're going to create an original query here. For instance, what was the total profit for the year and how does it compare to previous year? So this is the original query, and then I have this hypothetical query, or answer I should say. And so I'm going to use the augmented query generated, the function, and I'm going to pass the original query, which is this one here. And then I'm going to join those two queries, right? The original and the hypothetical answer. So original and hypothetical answer, and I'm going to print them out so we can see how those will look. So I'm going to go ahead and run this. You can see here we have this, what was the total profit for the year and how does it compare to the previous year? Very good. But then we have this total profit. Look at this. We got an answer. So we hallucinated. We used the large language model to create that answer. The answer is the total profit for the year was 10 billion and so forth. And by increased sales and successful cost cutting initiative implemented throughout the year. Very good. So now we have the query and we have the answer that was hallucinated, right? That was created, which is part of this technique. So now we are golden because we have those two. And so once we have those two, it's time for us to then pull all of that into our Chroma collection and query using those two disjoint queries, right? In this case, I call joint query, but it's original query and the hypothetical answer. So I'm going to say Chroma collection. I'm going to put in a variable result because I'm going to use that to just retrieve the documents, right? So I can say query. I can pack query text. What is the query text? Well, in this case, it's going to be joint query because that is what I got. So the original query and the hypothetical answer, which is what we just received from the large language model. Now, you could have created yourself a list of or one question for the hypothetical answer, but it's always nice to use the large language model because then it can create something that is more useful. You don't have to think about it. All right. So now we have this joint query, which is that. And then we say we want 5 results. And most importantly, we want to include documents as well as embeddings in our results. All right, because you will see that the reason why I want embeddings, you will see because we're going to use actually those embeddings to create a graph that will show the relationship of those embeddings visually so we can see how this works. All right, so then we have retrieved documents. In this case, I'm going to go ahead and show those retrieved documents. All right, so I'm going to print them out. Let's run. And there we go. So the idea, we are getting the documents that were passed through. In this case, we have the query, the original query as documents that we receive, as well as the generated answer, put them together, and then we pass them through our collection to say, okay, this is the query text, the joint query, and we want 5 results. So include documents and embedding. So we have all the documents that are related to the query. So we are seeing the query results from the answer concatenated with the query, the original query. Go through the vector database and we get the query results. So now that we have our retrieved documents, which is exactly what we want to project this data set on a nice graph so we can see the relationship. We can see the improvements that we have in the documents that we get that are related to the original query. And for that, we are going to import a few things here. So I'm going to Command V. I'm going to first of all create embeddings, go to the chroma, and we've seen this before, right? I'm going to get the embeddings because we're going to be using those. And then I'm going to use the UMap library to actually create the projections. And for that, we need to install, say pip install umap-learn. Okay, this library. Okay, it's all done. Put import umap so we can use it at the bottom here. And I'm going to say from helper utils import project embeddings. There we go. Okay, so now we have this projected dataset embeddings. Now notice that we're getting these embeddings here from our Chroma collection, because when we saved also embeddings along with other information. Okay, so that's the beauty. Okay, so I'm going to use project embeddings, and this is a function from our utils as well the umap transform. Okay, so next what we'll do, we're going to retrieve the embeddings. Okay, as you see there. So I'm going to retrieve embeddings from our results, which is our collection query there. And then I'm going to get the original query embedding by calling the embedding function and passing the original query that we saw before, and getting the augmented query embedding. This is for us to see the differences of the results that we get between original query embedding, in this case the original query, and the joint query, which is the original query, the query plus the answers that we hallucinated to put together. Okay, that's all we're doing here. And then we are going to create some projection variables here. So here I'm creating an object to project original query embedding by calling project embeddings and passing the same thing, the query embedding for the original, and passing the UMap transformer, and doing the same for project augmented query embeddings here, passing the actual augmented query embedding, which is what we have here. Okay, and then projecting the retrieved embeddings. So I'm just projecting them. All right. And next, we're just going to import matplotlib like such. We don't have that. Let's go ahead and pip install so that we're able to see the figures, see the graphs and everything. Okay, once that is all set up, then I'm going to go ahead and just plot everything. So now here I'm plotting the projected query and retrieve documents in the embedding space. So this is going to be just a 2D, and you know that embeddings, the vector space can be it's multi-dimensional. So but we're going to use 2D to facilitate so we can actually see the differences here. That's what I'm doing here, scatter and creating different points in our graph. And then I'm going to go ahead and show that graph. Okay, let's go ahead and run this real quick so you can actually see what we're talking about. So this is beautiful. So you can see here, this is a 2-dimensional vector space that shows all of the information that we have plugged in. So what we have here is the red X, as you see here, is the original query. And all of these gray dots are the dataset embeddings. Now the retrieved documents are close to the augmented query. What is the augmented query? Well, this is the augmented query. The orange X is the augmented query, which contains, as you remember, the hypothetical, in this case the hallucinated answer, and the original query. And then these green dots or circles here, these are the retrieved documents. So you can see that the retrieved documents are close to the augmented query in the embedding space, which is improvement. Whereas here is the original one, and we are really far away from all the retrieved documents. So that tells you that indeed this technique works. So the bottom line here is that the augmented query is closer again to the retrieved documents than the original query in the embedding space. It tells us that using hallucinated answer, which we hallucinated meaning we asked the large language model to create that answer first beforehand, was part of the query to improve the retrieval results because the augmented query is closer to the retrieved documents than the original query in the embedding space. Looking at this, you can see that is quite an improvement. Now, again, this is not perfect, of course, but you see that we can use it to refine the results that we get from our previous naive RAG. Using this technique here, then we get something that is a little bit more closer to the actual documents, right? The most relevant documents that were retrieved. So what I need you to do is to ask a different question and see how this graph will show the improvements between the original query and the augmented query. Okay, so we just saw how to use the query expansion with generated answers as an advanced RAG technique to generate potential answers to query using a large language model and to get relevant context. So essentially, we have the query, and then we pass that through the LLM to generate an answer. And then we combine all of that, so the query, original query, and the answer that we received to get query results. And then, of course, that helps to pass through the large language model and to get answer, to see how in a 2D dimensional space, how the documents, relevant documents, are closer to the augmented query instead of the original query. Now, what are the query expansion use cases? Well, this can be used in the information retrieval system or in the question and answering systems, as well as e-commerce search, and also the academic research, as we've seen. So what I want you to do next is to create different queries and look at the differences that are plotted so you can start seeing how query expansion with generated answers works. It's a really good technique. Obviously, it's not perfect, but you can see the difference in many cases that are not negligible at all. There are really good differences that perhaps you can see the power or the usability of using this query expansion as an advanced RAG technique. Okay, so now let's look at the query expansion again, but now with multiple queries. So the idea is that we use the large language model or the model to hallucinate or generate additional queries that might help getting the most relevant answer. Just like before, we have a query and we pass that through the large language model, and then we actually get more queries. So essentially, we use a large language model to suggest additional queries, and then we retrieve results for original and new queries through the database or vector space. And that's what we actually pass through. And then we send all those responses to the large language model for a final relevant answer. So that is the overall workflow, how the query expansion with multiple queries works. So essentially, we have more queries instead of one answer. In this case, we're actually creating queries as opposed of creating answers. In a nutshell, we have the original query analysis part that happens. So we're analyzing the original user query to understand its intent and context. And then we have the subquery generation. So this is where we generate multiple subqueries that expand on different aspects or interpretations of the original query. So we have breadth of different subqueries. Now, this can be done using synonym expansion, related terms, or contextually similar phrases. You could have in your organization or in your business, you could have a list of these subqueries, but we're going to use the large language model to hallucinate those subqueries. And then we have the document retrieval. So now we retrieve the documents for each subquery separately. That is the beauty here. And then we have the combination. This is the aggregation side of things, where we combine the documents retrieved from all subqueries, that way ensuring a diverse and a more comprehensive set of relevant documents. And then, of course, the response generation. This is where we use the aggregated documents to generate a more informative and contextually relevant response. Here are some use cases for query expansion. Exploring data analysis. So this could be a way of helping analysts explore different facets of data by generating varied subqueries. We have academic research. Again, we've seen this before, to provide researchers with different angles on a research question by generating multiple subqueries. Customer support. This helps in covering all aspects of a user's query by breaking it down into small specific subqueries. Healthcare information system, so helping with retrieving comprehensive medical information by expanding queries to include related symptoms or treatments and diagnosis. Let's go ahead and put all together in code. So I put together this expansion queries.py. You should have access to all of this anyway. And let's get started. So I went ahead and did some imports. So most of this actually is going to be exactly the same as we had before, but I'm going to go through again just for completion. Okay, so we've imported everything. We have the OpenAI client and everything is good. And first we are going to do what we did before, which is to read everything through using the PDF reader to get our data. Okay, so we get our data, Microsoft Annual Report, PDF, and extract those texts, okay, from the page. And we're going to filter the empty strings as you see here. Okay, so I'm not going to run this again. And then I'm going to split all of those pieces into smaller, right, chunks, as you can see here. And I'm using the recursive character text split from LangChain. And we're going to also be using the sentence transformers token text splitter as we saw before. So essentially really the same thing that we did before. Okay, use the sentence transformer to get split into tokens. As you see here, that's what we're doing. We have the text splits and we have all set up in this list here. We are looping through and adding that to the list of token splits. And next we are going to import ChromaDB and do all of that again. So I know this is kind of overkill, but I'm going to put all of this for completion. Okay, so now we're creating our embedding function using this sentence transform embedding function. And so we instantiated our ChromaDB client. Okay, and all of this is good. Next, we're going to add all of those embeddings into our ChromaDB. But first, we're going to extract the embeddings of the tokens as we did before, and we added all of those. Okay, we have the count there as well. And now I'm going to add the query, pretty much the same as we saw before. So what was the total revenue for the year? Pass that query through our collection to see what we get. So collection, query, we pass the query. Up till here, let's go ahead and make sure that we're actually getting the documents. So I'm just going to loop through all the retrieved documents and see. Okay, very good. The same thing we've seen before. We're getting all of our documents, at least 5. 1, 2, 3, 4, and 5. Next, let's have a multi-query function that will be responsible for generating the multi-queries. So the difference here is that in our prompt in this generate multi-query, we still pass the actual query, and the model is defaulted at GPT 3.5 Turbo. And here the prompt here, we're saying you're a knowledgeable financial research assistant and your users are inquiring about an annual report. But for the given question, propose up to 5 relevant or related questions to assist them in finding the information they need. Now, this is very important because everything is driven through the prompt. So your prompt should be something that you put some thought into it. And the important thing here is that you need to make sure that we have a prompt that encourages the model to actually generate related questions or queries. So make sure that the prompt must include different aspects of the topic and the variety of questions that will help the model understand the topic better. Provide concise, single topic questions without compounding sentences that cover a variety of various aspects of the topic. Ensure each question is complete and directly related to the original inquiry. Very important to have a well-refined prompt. Of course, we pass the prompt and the query, which is going to be passed through the function. Let's go ahead and generate the multi-query. So at the bottom here, I'm going to just paste. So I have the original query. What details can you provide about the factors that led to revenue growth, for instance? And so the augmented queries here, I call the generate multi-query and pass the original because that is what it needs. So at this point, I should get a result that will give me what I need. Step through and get augmented queries. Okay, so I'm going to just show here. So let's query through all the augmented queries we're going to get and print them out. And at the top, let's make sure that I have concat. Okay, very good. This is already commented out. Just going through the process, and soon we should see. And just like that, you can see we have our augmented queries. So here is the first one. How did changes in pricing strategy impact revenue growth? What role did new product launches play in driving revenue growth? Were there any specific marketing or advertising campaigns that significantly contributed to revenue growth? How did changes in customer demographics influence revenue growth? Did partnerships or collaborations with other companies impact revenue growth? This is wonderful. So you can see that our large language model was able to plug in from the query that we passed along, the original query. We're able to plug in and get at least 5 new queries, 5 new augmented queries. Now that we see that we have our augmented queries, because we looped through and we saw all of them, all of those were generated, let's go ahead and join or concatenate the original query with the augmented queries. Okay, let's go ahead and do that. Let's go ahead and print join query so we can see. Okay, so we can see that we have the augmented queries still loading. That's very good. But then we have this list that will contain each one of our augmented queries with the original query. Okay, so you can see here what details can you provide about the factors that led to revenue growth. And then we have the augmented query. What were the key products, which is the first one here. So for each one of these, we are concatenating or attaching to the original queries as well as the augmented query. So we are concatenating both of them. And you can see they're all in a list. Now we're going to go ahead and get this joint query, which will have, of course, the original query and the augmented queries through our collection, in this case, through our vector database and query. So let's do that. And there we go. So now we have retrieved results. And next thing, what we need to do, because we might get multiple duplicates. Now, because of the nature of things, we might end up getting multiple duplicates. We can now remove duplicates and essentially sanitize the list that comes from our retrieved documents from our collection.query here. Okay, so to do that, let's go ahead and so now we're going to go ahead and just go through and sanitize our lists to remove the duplicates. And let's go ahead and output results documents. Okay, let's go ahead and run this. So it should go and output result documents. For each query, we're going to add that query and then result and loop through and get each one of those results. Okay, let's go ahead and run this real quick. Okay, there we go. There's a lot here. Looks like gibberish, but that's exactly what we're doing. So we're outputting the results documents. So at this point, we have passed everything through the query, and now we're looking through and get the query results. So all the documents that we were able to retrieve through the queries concatenated with the query, the original query. All right. So the next step really is to go through, pull all that information, pass that through a large language model so we can get the answer. All right. So now what we can do is just plot everything so we can see the results, right, in a graph. So let's go ahead and project everything. Okay. So we pass the embeddings just like we did before. We're getting all the embeddings from our collection. And then we instantiating the UMAP transform so that we can have that to pass through the dataset embeddings and project embeddings to project everything. Okay, so it's the same thing we've seen before. So next we're going to visualize results in embedding space. So by creating the original query embedding and then the augmented query embedding so we can see the differences. We're going to project the original query and augmented queries in embedding space, but because of the nature of things, we're going to flatten the list of the retrieved documents to a single list, because the project embeddings expects indeed a single list of embeddings. So that's what we're doing there. And what we'll do next is we're going to go ahead and retrieve the embeddings themselves and result embeddings, just looping through all of them and get them. And we're going to go ahead and project those embeddings, the result embeddings, and UMap transform that we're passing through, as you see there. And of course, as always, we're going to go ahead and plot everything using the matplotlib. So we're going to have to import that. And then we're going to go ahead and pass it through the plot figure, the plot object, and project everything. Okay, let's go ahead and run, and we should see, if all goes well, something projected. Again, you can see here are our results. Everything is pretty much squished in. Red X, which is the original queries, and then we have the orange X's, which are the augmented new queries that were generated, okay, by the large language model. The green circles are the retrieved documents results by the vector database search, okay, and the gray dots are the datasets embeddings. Now, the retrieved documents are close to the augmented query. As you can see here, all these yellow or orange X's are the augmented query, and you can see most of them are really aggregated around the augmented query, which is really good. It tells us again that we're able to see the closeness, and not so close to the original one, even though there's this closeness between the original and the augmented queries here. But the actual documents that are relevant are agglomerated or are around the augmented query, as you see. Okay, much better. So you can see that we have 1, 2, 3, 4, 5, 6, I guess 6 augmented queries, 5 or 6 or something like that. And of course, we only have one original query. So this is probably better for you to visualize. So we see that with the query expansion, we are able to retrieve more relevant documents that we might have missed with the original query, which gives us a better understanding of the topic and helps in answering the original query, because the model generated queries, the hallucinated queries, have helped us in capturing different aspects of the original query and provide a more comprehensive view of the topic. So the model generated queries help in capturing different aspects of the original query. So now we have a more comprehensive view of the topic and can better answer the original query, especially for cases where we have complex topics like financial reports and so forth. Now, there's a downside to this. The downside of this approach is that the model-generated queries might not always be relevant or useful and can sometimes introduce noise in the search results. So it's important to carefully evaluate the generated queries and the retrieved documents. Okay, so in the next videos, we are going to tackle this issue of noise that I'm talking about in the search results by using a more advanced technique that will allow us to rank, in this case, all of these documents so we can get the relevant feedback. So, but before we move forward here, I would like for you to do a challenge. So what I want you to do is to play with different prompts and queries to see what results you get each time. So keep refining the prompt and see the results. So this is very important because, as we've talked about, the prompt is what guides everything for you to be able to get those multiple queries that are related to the query, which is going to influence, of course, the documents that you end up getting from the vector database. So we just finished going through the query expansion, in this case with multiple queries, which allows us to use the large language model to hallucinate or generate additional queries that might help us getting the most relevant answer. So this is the overall flow where we create queries from the large language model, and then we concatenate the original query with the augmented queries, we call it, and then we extract the relevant information from the vector database, these query results, and then we can use that to do all sort of things to get the actual answer. Of course, use cases for query expansion range from exploring data analysis, academic research, we've seen this before, customer support, healthcare information systems, and so forth. As I said, there are some downsides to this technique because there's lots of results. That means queries might not always be relevant or useful because we end up having noise. Hence, we need another technique to find relevant results. So once we get these results from this technique, we should probably go a little bit further and find what we just received as a result from this technique. Okay, very well. I hope you enjoyed this mini course. I made it for you and that you see the whole picture of RAG systems. Now, the idea here is that you take this and you build your own RAG systems and understanding now the techniques, the advanced techniques that you can use to make your RAG systems even better, so that they don't hallucinate as much and you get the correct or the closest information or pieces of information from your documents that then you pass through the large language model. So then you have a fuller response that you're confident that it is exactly what is being retrieved from the system. So thank you so much for being here. So if you're interested in learning more about RAG, about AI agents and Python and programming in general, I do have a channel called Vinci Bits. So it's right here. And also I'm working on a larger, more comprehensive course and or courses related to AI, large language models, and creating AI-based applications from zero to hero, right? And so if you're interested, should have a link somewhere in the descriptions where you can go and drop your email in the mailing list, in the waiting list, I should say. And as soon as I have everything set up, you will be the first one to be notified. So again, thank you so much for your time, and till next time, be well.